All right, ladies and gentlemen, let's have a look at how you go about taking care of this task of predicting chemical reactions. All right, let's make the answer key. Read all the directions. So you're going to identify the type of reaction, predict the product, complete reaction, balance the equation, specify all states of matter, and if a single or double displacement, predict whether the reaction would occur, work the full problem out even if it does not occur. And if you're typing, then this should be in a color different from the original text. So you read all the directions, say, I've read the directions, and we'll do as they say. All right, so anyway, let's do that. Identify the type of reaction. Let's start with this first one. Compound plus pure element, that is single displacement reaction. All right, does it occur? We'll get to that shortly. But we've got to predict the products and complete the reaction. So single displacement means we need to switch the parts that will switch with each other. So metal plus compound will element plus compound will produce element plus compound. So the aluminum will switch places with the zinc because aluminum makes a cation and so does zinc. So you're going to get aluminum sulfate, and you're also going to get zinc as your pure element. Now aluminum is a +3, sulfate is a -2, so you're going to have 2 aluminums and 3 sulfates in your formula because step 1 was switch the parts, step 2 is fix the formulas. So Al2, and then put parentheses SO4 and then 3 of them, and then this is the formula of pure zinc. So step 3, balance, as it says here. So 1 zinc, 1 zinc, 3 sulfates, let's put a 3 right here for 3 sulfates, and then 2 aluminums, and then 3 zincs. All right, that'll take care of that. So specify the states of matter. Okay, that will for single and double displacement reactions only. All right, so for zinc, this is going to be a solid because pure elements are solids, or rather pure metals are solids. For aluminum sulfate, we need to go to the solubility chart, and remember we look up the anion, the sulfate. Sulfates are generally soluble, that means aqueous, unless paired with one of these, and aluminum is not one of them. So since sulfates are aqueous and aluminum is not an exception, this will also be aqueous. Pardon my small writing, but this is going to be aqueous, that's going to be solid. Does it occur? We do not get that information from here. This is for double displacement reactions only to tell you whether or not it occurs. For single displacement reactions, this tells you whether or not it occurs. So does this occur? And by the way, I put an X here because I did specify the state of matter for each product. So does it occur? Remember, the pure element needs to be above the one it wants to replace. So aluminum needs to be above zinc on this periodic on this chart here, because aluminum wants to replace zinc. So is aluminum above zinc? Well, I find aluminum here, and zinc is indeed below aluminum, or shall I say aluminum is above zinc. So that's why I say, yes, this reaction will occur in real life. All right, so that's how it goes. We got to move on and do the next one, which is a double displacement reaction because it's 2 compounds. So, all right, let's write down what it would be. So we have sodium and carbonate. Well, now sodium's going to pair with the nitrate. So you're going to sodium nitrate, and the calcium's going to pair with the carbonate. So sodium is a plus, nitrate is a minus. What am I doing? I just switched the parts. I put sodium with nitrate instead of with carbonate. Put calcium with carbonate instead of with nitrate. So now I'm going to fix the formulas. Is this the correct formula for sodium nitrate? You're going to have 1 sodium, 1 nitrate in the formula, so indeed it is correct. Calcium is a 2 plus. Carbonate is a 2 minus. Turns out if they're the same charge, you're going to get just one of each. To show that more in detail, switch the charges, 2 carbonates, 2 calciums, and Ca2, CO3, 2, a 2-to-2 ratio becomes a 1-to-1 ratio. So it reduces. So anyway, that, in other words, that's also the correct formula. So it turns out these formulas are correct, just matching them up like that. And then we get a balance. That's that step right there. So I do notice that there's 2 nitrates here, so I got to put a 2 here for 2 nitrates, 2 sodiums, and there's already 2 sodiums there. 1 carbonate, 1 carbonate, 1 calcium, 1 calcium. So okay, that's balanced. Now, state of matter for each product. Remember, we look up the anions, so a nitrate and a carbonate. It says nitrates are always soluble. That means always aqueous. Oops, there you go. Now you can see it. Yeah, nitrates are always soluble. So AQ it is. This carbonate, it says carbonates are generally insoluble, which means solid. However, we look and see, however, there are some exceptions. This is found with calcium. So carbonates are generally solid. Is this an exception? Calcium is not in group 1, calcium is in group 2, and that's not calcium either. So calcium is not an exception, it's a solid. So there, we just specify the states of matter. And does it occur? For double displacement reactions, we determine whether it occurs by looking at the state of matter for the things in the reaction. And in this case, because something is not aqueous, we say yes, it occurred. The only way for the answer to be that no, it does not occur is for every single thing in both reactants and products to be aqueous. So if anything anywhere is not aqueous, then yes, the reaction occurred. All right, there. That being mentioned, we can move on to the next thing, which is this compound plus compound classic double displacement reaction. And as usual, you're going to switch pieces. So hydrogen goes with the hydroxide. So hydrogen goes with hydroxide. And then magnesium goes with chlorine. Now we fix the formulas, because now we've started by switching the parts. Now we're going to fix the formulas. So let me grab a white out, because that'll make things a little bit easier with this. All right. So I want to point out that if we're going to fix the formula, HOH is H2O, right? That's 2 hydrogens and an oxygen. So we can rearrange that formula to be what it really represents. Guys, HOH is H2O, it's water. And then MgCl, Mg2 plus Cl minus 1 magnesium, 2 chlorines. So 1 magnesium, 2 chlorines. That's fixing the formula right there. Use some common sense. Water's a liquid. And then MgCl2, so that's a chloride. So you look that up on this chart right here. So that goes under halides. Halides are soluble unless paired with these. Magnesium is not one of the exceptions. So soluble means aqueous. So I put AQ. Does it occur? Answer is yes, because one of the products is not aqueous. Water is just a liquid. All right, I have specified the state of matter for each product, and there we go. Oops, silly me. I almost forgot to do one thing. I need to balance the reaction. Let's see, 1 magnesium, 2 oxygens, 2 hydrogen, and then 2 chlorines. So anyway, and then 2 hydrogen, 4 hydrogen. Let's see, 2 hydrogen right there, plus 2 more is 4 hydrogen, and then just double checking 2 oxygen, and then, yep, that all looks good, that's balanced. So 2 HCl's plus 1 MgOH2 makes 2 H2O's and 1 MgCl2. All right, next. What is this? Another double displacement reaction, because look, it's 2 compounds reacting. All right, double displacement it is. So sodium gets paired with hydroxide, and potassium goes with sulfate. So potassium and sulfate, and sodium and hydroxide. Potassium is a plus, sulfate is a 2 minus. So you're going to get 2 potassiums and 1 sulfate, so K2SO4. Sodium is a plus, hydroxide is a minus, so that's 1 sodium and 1 hydroxide. So that's the correct formula. So we can just go balance this now because we have switched the parts and now we fix the formulas. Now we balance. So 2 sodiums, 2 sodiums, 1 sulfate, 1 sulfate, 2 potassium, 2 potassium, 2 hydroxide, 2 hydroxide. Okay, that does it. So that's the balancing. Now, let's specify the states of matter because we need that in order to know whether or not this occurs. Potassium sulfate. Sulfates are soluble. Potassium is not an exception. Therefore, this is aqueous. Hydroxides are not soluble. However, they are soluble with group 1, and sodium is a group 1. So, therefore, these are also aqueous. And you'll notice that means aqueous, 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 aqueous all around. Does it occur? No, it doesn't. Specify the products anyway, even though it doesn't occur. And there we go. We have specified the physical state of each of the products. All right, next, reaction type. One single reactant makes a couple of products in a decomposition reaction. Metal carbonates produce metal oxides and carbon dioxide when they decompose. Li plus 1 and then O minus 2, Li2, O1. So 2 lithiums, 1 oxygen. So Li2O and then CO2. All right, so let's double check on that. 2 lithium, 2 lithium. 3 oxygen on this side, 3 oxygen over here, 1 carbon, 1 carbon. It is balanced, and that's it. We're done. All right, next. We have CH2O plus oxygen. So this is a combustion. If it reacts with oxygen, it's combustion. We're not going to call it synthesis, though, because if it reacts with oxygen, it's only synthesis if it's a pure element reacting with oxygen. That's not a pure element, obviously. Okay, so if it contains carbon, it will produce CO2. If it contains hydrogen, it will produce H2O. So let's balance this out. 1 carbon, 1 carbon. That's 2 hydrogens. That's 2 hydrogens. That's 3 oxygens. Oh, that's also 3 oxygens. Hey, look at that. It turns out this thing is already balanced as written. All right, we're done. All right, reaction type. You have 2 pure elements. When they react, that is a synthesis reaction. Okay, so that means barium will bond to nitrogen. And since barium is a 2+ and nitrogen is a 3-, you're going to get 3 bariums and 2 nitrogens in that formula. All right, and that's it. Almost, anyway. So then we just got to balance. So 2 nitrogen, 2 nitrogen. That's good. 3 barium, 3 barium. Now it's really good. All right, that's it. Next, chlorine and strontium iodide. What kind of reaction is this? We have a pure element plus a compound. That is going to be a single displacement reaction. All right, now this is actually a typo on here, and hopefully you students will get a corrected one because it should also have this stuff. Does it occur, and specify the states of matter. So, or actually maybe I can see why, because you might not necessarily know what the state of matter is for this one. But nonetheless, we can predict whether or not it's going to occur, and we'll do that too in just a sec, because we can do that for single displacement ones. All right, so for chlorine, it's going to switch places with the iodine because chlorine makes a minus ion, and so does iodine. So chlorine switches places with iodine because it's like iodine, which means chlorine attaches to strontium, and then iodine becomes an element on its own. So strontium attaches to chlorine. Remember, SR goes first in the formula because it's the positive one, and then iodine becomes an element on its own. So iodine is one of the Hofbrinkel diatomic elements, so Hofbrinkel, I2. And then strontium is a +2. Chlorine is a -1. So you're going to have 1 strontium and 2 chlorines in that formula, like this. Okay, so that's fine. So strontium chloride and iodine. Now, I suppose perhaps the reason why I may have set this up this way is because this might be a reaction happening in a strange environment, so actually maybe I'm seeing why I put it this way. But nonetheless, if this were in water, you could look it up on here and find chloride. Strontium chloride should be soluble, so if this were in water, it would be AQ. However, I suppose you probably would have no way of knowing that iodine is a solid at room temperature. So perhaps that's why I didn't ask people to specify the states of matter for this one, because you wouldn't know. But nonetheless, that's what it would be if it was in water. And actually, this does dissolve in water also, so that we're not going to worry too much about that. But would this actually happen? That is a totally legitimate question. Will it occur? That we can completely answer, because we got to say, will the pure element replace this? So will chlorine replace iodine? Well, the pure element must be above the one it wants to replace, so chlorine needs to be above iodine. We'll ask, is that true? So look at the activity series for nonmetals, and look, chlorine is indeed above iodine. So will it occur? Yes, it sure does. All right, let's continue. Now let's look at number 9. My first attempt at this, I actually made a mistake, so I'm going to replace it with this. The reaction here would be a double displacement because we have two compounds, so double displacement it is. That means the zinc will go pair with the nitrate, the tin will go pair with the carbonate. So you're going to have some combination of zinc and nitrate, and you'll also have some combination of tin and carbonate. Now, in order to figure out what that is, you're going to have to decide, well, at first you got to know the charge of zinc in order to figure out what this formula is going to be, but you also got to figure out the charge of tin in order to find this formula. So we're going to do those things first, balance and everything, and then when it's done, we'll be able to look at the solubility chart to determine what the states of matter is for all of these, and then, forgot to include aqueous there, and then whether or not it occurs will come out of us figuring out whether everything is aqueous or solid or whatever. And I'll show how you could have determined this even if it hadn't already been given to you on the worksheet, and same for this. All right, so let's find the formulas. So tin is assumed to not change its charge from start to end. So tin is paired with 3 nitrates. Each nitrate has a -1 charge. There are 3 of them, which means -1 times 3 is a total of -3 charge, which means the tin must balance it by being a +3, which means here the tin is also +3. So SN 3 plus and CO3 2 minus is what our combination is. You put the 2 down here, there's going to be 2 tins in the formula. Put the 3 down here, there will be 3 carbonates in the formula, meaning that this is the formula of the tin with the carbonate. Oops, forgot the little 2 right there. And then here, zinc is a 2 plus, that's something to be memorized. And then NO3, nitrate, is a 1 minus, so you're going to have 1 zinc and 2 nitrates in the formula, giving that. And then, okay, that's the formulas, now we just got to balance. So let's see, that's 2 nitrates, 3 nitrates. Oh, okay, well, I'll just put this 2 right here. I'll put this 3 right here. Switching the subscripts is a good way, quick way to balance, because we got 6 nitrates and 6 nitrates. 2 tins, which is good because there's 2 tins. 3 zincs, which is going to need to be fixed. We'll put 3 zincs, and that means we got 3 carbonates, but that's okay because we've got 3 carbonates. All right, so that's the balancing. Now, does it occur? We need to go look that up on the chart in order to determine whether it occurs. Remember, you look at the solubility chart. Now, how did I know to put nitrate? I'd forgotten to include that from the worksheet, but how could you have determined this is aqueous aside from the worksheet? Because you look on here, all nitrates are soluble, which means all nitrates are aqueous, and there are no exceptions, which means everything with a nitrate is aqueous. That means not only this one, but this one is aqueous also. Now, as for carbonates, let's look at that. Carbonates are not soluble. So in terms of what that's going to be, carbonate should be soluble, or should only be soluble with a group 1 or an ammonium. So the deal here is that carbonates are only soluble with group 1 or ammonium. That's not group 1, that's some other group, and that's not ammonium, so it's not soluble. Therefore, we put solid, because insoluble means solid, and this is not an exception. So because there's something there that is not aqueous, we are going to say that yes, this reaction does occur. We've specified the states of matter, and just as a little side note, the version of the worksheet that we're using this year at least says aqueous for zinc carbonate, but according to this chart, carbonate is not soluble and zinc is not an exception, so that is actually a typo, and this actually should also be solid. Not that that changes anything, it means the reaction does occur because these are both solid, so it just turns one solid into another. Well, all right, onward. Okay, let's continue. Iron chloride and sodium hydroxide. Full balanced reaction. Iron 3 chloride, Fe plus 3Cl is a minus, chlorine's a minus. So 3 chlorines, 3 chlorines, 1 iron. So FeCl3 plus sodium hydroxide, NaOH. Sodium is a plus, hydroxide is a minus. So 1 sodium, 1 hydroxide in the formula. We got to recognize that this is double displacement reaction. And so that means the iron is going to pair with the hydroxide and the sodium is going to pair with the chloride. So you're going to have sodium and chlorine pair, and you're going to have iron and hydroxide pair. So if iron is a 3+, that means you have iron 3+ and hydroxide pairing up. That's 1 iron, 3 hydroxides, so let's do that. And sodium is a plus, and Cl is a minus, so that's 1 sodium and 1 chlorine, NaCl, so that's fine right there. So let's balance this reaction. There is 1 iron, 3 chlorine, which makes 3 sodiums, which makes 3 hydroxides, and 3 hydroxides, so there we go, it's fully balanced with 1 of these, 3 of these, 3 of these, and 1 of these. Let's find the states of matter so that we can figure out whether it occurs or not. So we're going to need to find the states of matter for both reactants and products this time. So chlorides are soluble unless with lead or silver or mercury. So this is not one of the exceptions, therefore this is an aqueous. And this one is also aqueous. Both chlorides are aqueous. As for the hydroxides, they are solid unless with group 1. So this is group 1, so that means this is aqueous because it's not solid because it's sodium's an exception, it's a group 1. And then what about iron? Is iron an exception? No, it's not, which means the general rule applies, which means this is solid. So we have something that isn't aqueous, therefore yes, it occurs. And we have successfully specified the state of each thing. All right, and we actually, I know it says product, but you got to specify state of matter for the reactants, because if you had all aqueous here, but if you had a non-aqueous here, you would still say it occurs. All right, so this one, classic single displacement. All right, let's find out whether or not it occurs by first predicting what it would make. Zinc replaces lead, lead replaces zinc because they are both going to be cations. So zinc nitrate, you may remember we did it earlier, but let's just as a reminder, zinc is a +2, nitrate is a -1. So you're going to have 1 zinc and 2 nitrates in the formula. And then pure lead is just Pb. So there we go, that takes care of the formulas, so that's fine. Now for the balancing, 2 nitrates, 1 lead, 1 zinc, 1 zinc. All right, it's balanced as written. Does it occur? The pure element must be above the one it seeks to replace. So zinc must be above the lead that it replaces. We check on here. Is, again, zinc above lead? So there's lead, there's zinc. Yes, zinc is above lead. Therefore, yes, this reaction would occur in real life. All right, let's specify the state of matter. A pure metal is solid. Zinc nitrate. Nitrates are always soluble with no exceptions. And if they're soluble, then it is aqueous. Okay, all right, now for number 12. Let's see, this reaction type is a single displacement with our pure element and a compound, and the pure element is not oxygen. So this is single displacement. Now, this single displacement reaction means that the silver will switch places with the nickel because silver is a cation, and nickel also makes cations, meaning you have pure nickel and then the combination of silver and chlorate. Now, silver, let's that by the way was switching the parts. Now we got to fix the formulas. That's step 2. So silver is a plus charge, chlorate is a minus charge, and then when you switch the charges, what you get is one of each, meaning that actually this is the correct formula for silver chlorate, meaning that if you have 2 chlorates here, our third step is to balance. So 2 chlorates here means 2 chlorates here, which means 2 silvers, and so we put a 2 here, and thus we have 2 silvers. 2 silvers plus 1 nickel, 2 chlorate makes 1 nickel and 2 silver chlorates. All right. Next question, will it occur? In order to find that out, since it is 2 metals switching places with each other, you consult the activity series of metals. The pure element must be above the one it wishes to replace, so silver needs to be above nickel for this to work. So we look on here and we find there's silver, and it is not above nickel. In fact, the other way is true. Nickel is above silver and not below it. So the pure element is not above the one it wants to replace. Therefore, we say no, this reaction would not occur in real life. Now, final thing, it did ask in the instructions to specify the state of matter for each of these things. So pure metals are going to be a solid. And then as for these things, these are chlorates. So we look on the solubility table and we find chlorates. Let's see, there it is. And then it says chlorates are soluble. That means aqueous with no exceptions. That means all chlorates, no matter what they are soluble, which means this is aqueous and this is aqueous. However, because these are not double displacement reactions, that has no bearing on whether or not the reaction occurs. It's merely just practice using that table. Okay, moving on. Specify the state of matter. Calcium metal plus perchloric acid. Calcium metal is calcium. Perchloric acid, acid starts with H. Perchlorate is ClO4. And then H is a plus, ClO4 is a minus, so it's 1 hydrogen, 1 ClO4. So calcium plus HClO4. What is this? Metal plus compound is single displacement. Does it occur? Well, we can check on that. I've solved the rest of these before telling whether or not it occurs, but for single displacement, you actually can tell whether or not it occurs even before you solve it. So calcium needs to be above hydrogen because calcium and hydrogen are going to switch places. So is calcium above hydrogen? There's calcium, and it's well above hydrogen on the list. So yes, this will occur because calcium is going to switch places. Calcium joins with chlorate, and the hydrogen comes out to become the pure element. So hydrogen is a pure element. Calcium bonds with the chlorate. Now that was switching the parts. Let's fix the formulas. Formula of hydrogen is H2 because it's a diatomic element. Calcium is a plus 2. Perchlorate is the -1 charge. So 1 calcium and 2 perchlorates. So I got to put parentheses and a 2. All right, let's see. So I'm going to put a 2 here because that gives 2 hydrogen, 2 hydrogen, 2 perchlorates, and then 1 calcium, 1 calcium. So we're good there. Let's specify the state of matter. Sure thing. Hydrogen's a gas. Might have been a harder one to get. But yeah, hydrogen's a gas if you didn't already know that. And then as for calcium perchlorate, okay, perchlorates are right there. It's soluble with no exceptions. So that's aqueous. And hydrogen's a gas. Pure calcium's a metal, and then perchlorates are always soluble. All right, we specify the state of matter. We had to do it for the products, but just for fun, I did it for the reactants too. All right. Ooh, a decomposition with just one reaction. That tells me it's decomposition. And the metal hydroxide will decompose to make the metal oxide and H2O. And barium is a 2+, oxygen is a 2-. 2 bariums, 2 oxygens becomes, oops, there you go, barium oxide. So that's actually correct. 1 barium, 2 oxygens balances with 2 oxygens, 2 hydrogens balances with 2 hydrogens. So that's it. Does it occur? That's actually a typo. I'm supposed to be asking that. So you just assume if this was for some reason to appear, you would just say yes. But that was actually a typo not intended to appear there. And then this doesn't really need to happen either. All right, iron and copper. All right, let's look at this one. I made a mistake on the first try through, so we'll give this a second look. Now, it gives the hint, iron plus copper 2 sulfate, you got to turn it into an equation, and we're going to assume that iron takes a +3 charge. As mentioned in the original question, it says assume iron takes a +3 charge. So iron is just Fe, copper 2 sulfate is copper with a 2+ charge, and then sulfate is SO4 with a 2- charge, which, by the way, when you switch the charges, that means 2 coppers and 2 sulfates. And if you've got 2 coppers and, sulfate, 2 sulfates, that simplifies down to CuSO4, because a 2-to-2 ratio is the same as 1-to-1. So therefore, when we take this, what we're really getting is Fe plus CuSO4 makes what? It says assume iron takes a +3 charge. So that means you're going to get iron with a +3 charge and sulfate with a -2 charge. How did I know that? Because iron and copper will switch places because they're both cations when they form ions, which means the iron pairs up with the sulfate and the copper becomes a pure element. So you'll get 3 sulfates and 2 irons in the formula resulting from that, and then copper will be your pure element. So pure copper, and then iron 3 sulfate has Fe2, SO4, and then 3 of them. So that's where it begins. Now we can of course balance this. If we're going to do that, then let's save the pure elements for last. Let's do sulfate first. So 3 of these makes 3 of these, which makes 3 of these. Because 3 sulfates, 3 sulfates, 3 copper, 2 iron, 2 iron. All right, now that being what it is, let's look at the next thing. This is a single displacement reaction, and we need to figure out whether or not it occurs. We also need to specify the state of matter for each product. So pure metals are solid. It was not told what these are, so I'll show you how to get it for both of them. The state of matter for sulfate, you can get that off of the chart that I have somewhere around here. And if I can't find what I did with my own chart, here it is. Sulfates. So you look at the sulfates on here, and you find that sulfates are soluble. They're under the soluble category, which means that sulfates are assumed to be aqueous unless paired with one of these. Notice, neither iron nor copper are on this list, which means sulfate just follows the rules, which is soluble. So you assume they're both aqueous. All right, now that being what that is, one of the other things we got to do is decide whether or not it occurs. So in order for it to occur, the pure element must be above the one it wants to replace on the activity series of metals, in this case because they're metals. So that, in other words, iron needs to be more reactive than copper, which means iron needs to be above copper on this list. So there's iron, and there's copper way below it. So since the pure element is above the one it wants to replace, see, pure element is above the one it wants to replace, then we say, yes, this occurs. All right, let me just double check. Yep, that should be everything necessary for this particular one. And let me just reemphasize, because you do have to write it on your paper, that this is a single displacement reaction. And that's why we used the chart that we did. All right, onward. So there you go. I specified what state of matter it is. And okay. Now, water and potassium. Water, H2O. Potassium is just K. So H2O plus K. Element plus compound. This is a classic, single displacement. So this is a difficult one, but in actuality, if based on what we taught you, you would be expecting potassium and water to make, like, the potassium switches places with the hydrogen to make potassium oxide, and then hydrogen gas. This is what you would expect. Unfortunately, it's slightly more complicated than that. It actually turns out to be, this is a challenge one, it's potassium hydroxide. It only splits one of the waters off, but it does make hydrogen gas, or sorry, it only splits one of the hydrogens off. So it replaces one of the hydrogens, not both. This, again, is a challenge problem. We wouldn't put something quite this complicated on a test, but what it does is, again, it switches places with one, not both of the hydrogens, so it makes potassium hydroxide. And then if you're going to balance that, and I put H2 because the formula of pure hydrogen gas is H2, we need to do a little bit of adjustment here. All right, so because if I do that, then that's getting better, and then we can have two of these. And because, why did I do that? 2 oxygens, 2 oxygens. And then the reason why I did that was because if I have a 2 here, I can have 2 hydrogens plus 2 more for a total of 4. And this is 2 hydrogens times 2 for a total of 4. So that balanced the oxygens and the hydrogens. And of course, you can't forget to put a 2 to balance the potassiums. And there you go, everything's correct. So does this occur? In other words, is potassium above hydrogen on this single displacement table? So there's potassium way up here, there's hydrogen way down there. Yes, it sure does. All right, potassium hydroxide. Hydroxides are not soluble unless paired with a group 1. Potassium is a group 1, therefore it's soluble, it's aqueous. Hydrogen is a gas. All right, so there you go. I specified the state of matter for each product. But yes, it sure occurs because potassium is above the hydrogen that it replaces. All right. Rewrite the word equations as full balanced equations that predict the products. Combustion of glucose. That means C6H12O6 plus oxygen. That's what combustion means. It reacts with oxygen. And if it contains carbon, one of the products will be carbon dioxide. If it contains hydrogen, another product will be H2O. So there we go. Let's balance. 6 carbon, 6 carbon. 12 hydrogen. If I put a 6 here, that makes 12 hydrogen. Now for the oxygens. Let's see. This is 6 oxygen. That's 8 total oxygens on this side. This is 6 times 2 is 12 oxygens. And then plus, so it's 12 oxygens plus 6 more for 18 oxygens. All right, so I need to get 18 oxygens over here. I've already got 6, so 18 minus 6 equals 12 more. So I need 12 oxygens out of this. So if I put a 6 here, that is indeed 12. And indeed, 6 times 2 is 12 oxygens plus 6 more is 18. So that's 18 oxygens here. And then this is 12 plus 6 more is 18 oxygens here. So 18 oxygen, 18 oxygen. Let's just double check. 12 hydrogen, 12 hydrogen. Let's just double check. 6 carbon, 6 carbon. So there we go. That's good. That's this one all worked out. Finally, decomposition of mercury 2 oxide. So mercury is Hg with a 2 plus if it's mercury 2, and then oxygen is a 2 minus. So that is Hg2O2, which becomes just HGO. So decomposition of mercury 2 oxide. Unless it says with heat, you don't need to put that delta above the arrow. Even if maybe it does in real life, unless it says so, don't put the delta. Decomposition is going to, unless it's one of the special ones you memorized or saw in the notes like this one, then you just assume that it splits into the elements it's made out of. So mercury oxide becomes mercury and oxygen. So pure mercury would just be written as that, and then pure oxygen would be written as that. And then we just balance in order to make it work. So we put a 2 here, that way it's 2 oxygens and 2 mercury, so we put a 2 right there. And that would be it. That's how you do it. All right, ladies and gentlemen, happy study.